Okay, well, it's great to have Maulik back with us. I don't know, after ages. Last time you spoke was when you were at ICER, Pune. I think so. I think it's been what, 15 years? Okay, I don't know, 10 years. Yes. But anyway, great to have you, Maulik, and look forward to your talk with a very provocative answer. So,
okay, thank you. And it's a pleasure to be here, and thank you for the opportunity to speak. As I was just talking about Sandeep, I'm from Mumbai, from the time when it was called Bombay. And so I grew up here, and so there's really no excuse for me not to come here more often. In fact, my connection to TIFR goes back over 50 years. How's that? Because my mother was a postdoc here, and my father was working with Vikram Sarabhai. I was born here, and my first year was in the TIFR department.
No kidding.
So I don't have any memories of that. So they say. So today, for the last 5 or 6 years, I've been thinking about why we haven't seen any quantum effects in gravity. And of course, Einstein's theory is over 100 years old. And it's shocking and actually, frankly, a little embarrassing that every single observation ever made, give or take a cosmological constant, is in 100% in accordance with Einstein's theory. And that's shocking for a variety of reasons. We know many, for theoretical grounds, that Einstein's theory is only the first in a series of higher curvature terms. We should know that there should be other corrections, and of course, most of all, it's just a classical theory. And everybody in this room knows that gravity must be quantized. This seminar series is even called Quantum Space-Time Seminar, but we have no evidence for it. So I've been thinking about that. Most of my work on this has been with my advisor and now colleague, Frank Wilczek. And there's a sort of rotating cast of postdocs and PhD students involved. Is this the pointer? So this work here was done in particular with my current student, Arunima Das. She's fantastic, third-year student. And then with my former postdoc, Rafael. Okay, so what's the problem? Why is quantum gravity so hard to observe? Well, from a theoretical perspective, we have sort of the full quantum gravity, which is string theory. And then we have a kind of gravity as a field theory of the helicity to fields. So in this case, what we know is that we don't really have a clear prediction. We have a heavy reliance on ADS. We have the Asian variant observables are not even clear because it seems to be there's, how do you reconcile the diffeomorphism and variance with local observables? The calculations are often not in 4D, whether it's in 10 dimensions in string theory or in 2 dimensions with JT gravity. And then sometimes in the status of the gravitational path integral, which we use all the time, is unclear. It doesn't even converge if you equirotate.
Just to give you a slight hard time, if the tensor mode is seen in CMB, etc. experiments, would you say that that's an indication of gravity?
Yes.
And that's a pretty clear calculation.
Yeah, that's right. That's right. So to be sure, there are, particularly in cosmology, I think, there are, if we had found B modes that have a clear origin from cosmology, that would be. Because I think for some dimensional analysis, you have to have an H-bar.
Yeah, that's right.
So then, perturbative quantum gravity, we know from effective field theory that loops are suppressed by power event line, which is an enormous thing in our units. And gravity is too weak, and single gravitons, although there been some recent excitement about this, are probably undetectable. There's a famous paper by Dyson saying we'll never detect gravitons. So this does not look very promising.
And sorry to interrupt again, but why is it? It's just because it'll require an experiment of incredible precision to see a single gravity.
Maybe we can talk about that particular. There are several hidden assumptions in Dyson's argument. The gist of it is that he says, well, in a typical gravitational wave, in one volume, one wavelength cubed, there are about 10 to the 37 gravitons. He just estimates that, and then from the energy density. And then, therefore, to see one out of those 10 to the 37, you need 37 orders of magnitude improvement in sensitivity. But that's a flawed argument. You don't need to see individual gravitons to detect their presence. Just like in Brownian motion, we don't need to see one kick to see the collective effect of that. So I think there are some assumptions there that don't hold up. But that was good. Okay, so this doesn't look very good. Well, let's see what we can learn from electrodynamics. So how do we know actually that the electromagnetic field is quantized? And if you look at the collection of sort of smoke, most of these are smoking guns. I was very careful about this. I didn't include the photoelectric effect. But there are a bunch of phenomena like photon anti. These may or may not be familiar with you, but the takeaway is that all these phenomena, many of which are quantum optics phenomena, hi Shiraz, are tree level, except for the Landship. So they are. So if you ask what people in quantum optics are doing, they're effectively doing tree level calculations in states that do not look like solutions to Maxwell's equations. Right? Like if you have a Fock state with one photon, there's no solution of Maxwell's equation that classical Maxwell's equations that corresponds to that. So the trick here is that if the state of the electromagnetic field is quantum, if it has no classical counterpart, then you will see quantum phenomena at tree level and there is no Planck suppression. Okay? So in the case of E&M, we can produce these states, right? In gravity, sadly, we are just given states. We don't really have control over tweaking the gravitational field state. But the same could be true for gravity. If this, depending on the state of the gravitational field, the quantum state of the field, there could be phenomena, observational signatures that are not, that do not require loops.
Okay. And again, sorry, these are all an aside to your main talk, but colleagues of ours here who have been studying the photoelectric effect, and they say, this is all old work, that it's true, the photoelectric effect per se doesn't establish a single photon, but you can look at the jitter. If you look at the spectrum more carefully, there's a kind of jitter which does arise due to quantum effect. So sort of slight recall.
Absolutely, yeah. And in fact, jitter is the key word for this talk.
Can you explain this state of the electromagnetic and no classical counterpart? What does that mean?
So, so normally, if you say what is a state, quantum state that looks classical, okay, so normally you would think a coherent state for a harmonic oscillator. And there are a variety of reasons for that. You can, which I think I will get to, such as that it the wave function doesn't disperse at a high occupation number. Of course, it saturates on certain principles. So those are properties of the coherent state. Those are not properties of a single photon state, right? Because
so even with the wave, we would say that the electromagnetic wave,
classical
electromagnetic wave.
What about it?
That would also be a coherent state.
Yes, that's right. Yeah. But not a single photon state or entangled photons or something like this. Okay. So that's the idea. So the key loophole, which might get us out of this Planck suppression effective field theory arguments, is that there might be potentially observable tree-level quantum gravity signatures if the quantum field is not a coherent state. And this has been my work for about 5 or 6 years, where we said, given a particular quantum state, what kind of signatures would we see? And so I worked on that, and the upshot of that, to look ahead to the end of the talk, is that if the gravitational field is in a squeeze state, then you will see there will be very distinct signatures at interferometers. Now, the obvious next question is, why should the gravitational field be in a squeeze state? And that's really the subject here, where I'm going to say that actually it's very normal for the state of the gravitational field to be not just a coherent state.
So just coming back to Abhijit's question.
Yeah.
If there was a probability distribution of classical configurations, would you call that classical? No.
No, that's you mean a stochastic distribution? That's
right.
not
So with probability something in probability.
Yeah, that's not a quantum.
That's not
quantum. And in fact, one of the problems, if you really want to be difficult, you can say, how do you distinguish a truly quantum phenomenon from a stochastic? And that's very hard. And I don't think we're anywhere close to that. For the quantum optics, there is a way to do that.
Yeah. So, but just trying to make that more precise, there's this thing that Onkar has been educating us about in quantum mechanics. For instance, there's this thing about the Wegener function. When the Wegener function is everywhere positive, then you can always make a positive sum over classical configurations that reproduces the dynamics.
Right.
So is that a way of distinguishing that if you look at a density matrix for your configuration and look at its Wegener function, look for positivity of that?
I think that's we're not at that there yet where we can say, this is clearly have to be quantum. So I'm going to find phenomena that quantum mechanics predict something, but whether you could be perverse about it and cook up a classical configuration that will mimic that, probably yes, I'm not.
I mean, just to come back to the example of the beam mode,
Yeah.
I mean, you put in the numbers, and as you said, you have an H bar there, without which in conventional theory, you can't explain the tensor perturbations, right? So just, we can take that as a guideline and say, look, if you have a phenomenon which, does not admit a good H bar going to zero explanation, then we take it to be a
That's right.
one, given our current understanding.
Yep. I mean, this would be next level, right? You can first you want to make a prediction and then see if it's observed, and then you can see whether.
But just one last and then sorry for interrupting. I wanted to understand that really a thing that's really quantum is interference, right? That's a completely quantum thing.
That's classical waves interference.
Classical waves.
No, but the wave function for the wave. Yeah.
I would say it's things like Bell's inequalities and so on. If you really want to push it, right?
Maybe.
I think it's.
But what I was asking is that say you've got a state with a cricket ball here and a cricket ball there.
Yes. Yeah.
That's like very non-classical.
Yeah.
However, if that gets entangled with the air molecules here and air molecules there, then that no longer can interfere.
Right.
And that would then be described by density matrix for the ball, which is like completely classical.
Right.
And will your criteria be able to distinguish these things that can interfere and cannot?
Right. So fortunately, because gravity is so weakly interactive, it doesn't actually decohere that easily. So that's the good news. Now, we haven't really tried to. I think the set of whether nature could be deceiving us is not right now this kind of thing we're considering. So it's possible that there could be other effects that will reproduce that, and that could be something like what you just said. Now, as I said in the beginning, a century of observation says that Einstein's equations are obeyed beautifully. But I'm going to argue that this doesn't mean necessarily that the state of the gravitational field, the quantum state, is actually coherent. So let me remind you about these states. So coherent states are certainly very classical. They are certain in the sense of most classical states. They saturate the uncertainty principle. They have a non-dispersing wave function. They have high occupancy. They also have the expectation equal in the classical solution, but that's true for all states by Ehrenfest's theorem. So these are the properties of a coherent state. And so we sort of naively say, classical dynamics means the state is coherent. But there are other states, another class of states called displaced squeeze states, which have all these properties. Okay. So the question about whether the nature has a coherent state or one of these displaced squeeze states is not just evident from saying we've seen Einstein's equations.
You're going to tell us what it
I'm
is.
going to tell you what
What squeeze
Yes.
is.
More generally, would you say that Gaussian states? The squeeze states I imagine now.
Yes, that's right. That's right.
So there's another notion that people talk about in the context of classical analysis quantum, which is contextuality. Does that play any role?
I'm not sure.
We'll have to educate us up to that's what that is.
Related to this very.
Yeah, it's related to Bell's
Well, Bell's inequalities are more like entanglement, right? This is about measuring the set of observables and two such sets. Those sets, let's say, happen to be non-mutually commuting with each other.
Right.
Then you cannot explain their measurements as coming from a statistical ensemble.
Yes, yes. There are many things that have been shown to be not reproducible. Yeah, exactly. So, for example, also sub-Poissonian statistics. That means that if you have that cannot be done by any.
But you're so
And there, these coherent states play a big role in that discussion also.
Well, they form a basis, so you can actually take any quantum state and write it into.
Sorry, I mean, just generic squeeze state, at least that I know of, I wouldn't call it a classical state, right? I mean,
Yes.
as opposed to a coherent. And it is a Gaussian.
Yes, so this is what I mean.
The huge delta X is squeezed and
Exactly.
P is large.
But it's the wave function is still low. It sort of oscillates. It doesn't fall apart with
Doesn't
time
fall
elevation. And so that's what I'm calling a quantum classical state in a way, because it behaves classically. But if you look at the variance and so on, you'll see something that doesn't look
Right. The variances can be
very large.
Very
That's
But
right.
it still saturates the uncertainty.
Yes.
It saturates it, but by reducing in one. And
Exactly.
I'm just saying it's got huge fluctuations about the mean.
That's right.
Unlike a coherent state where you can make them very small,
Exactly.
over root n. So far.
So that's the point, that if we have these squeeze states, then they have this feature which is different from classic coherent states, which if you were to measure that variance, you would see, this is something different. And whereas, if you didn't measure the variance, you were just looking at expectation values and so forth, they would be consistent with what we already know. Okay, so I want to now tell you about how these states are produced. We can start with any state we want, but really these states are produced by sources.
So just to make sure that we are talking about the state of the gravitational field, right, as opposed to the wave
That's right.
being this coherent of that.
Well, you can always take you can take a state and write it in various ways, and you can write a wave function for it, a wave function now in this case. But yes, I'm talking about a state of the gravitation.
So 1K, well, that's one harmonic oscillator, and what its state is.
Yeah, the full thing is a Fock space state, and you can decompose it into harmonic oscillators, as I will. All right. So indeed, everything begins. All good ideas begin in the harmonic oscillator. So this is the plan of the talk. I'm going to describe in some detail coherent states, squeeze states, how they're produced for a simple harmonic oscillator. Then we will talk about gravity, and finally signatures of experimental signatures. Okay, so the upshot here is, if there are time-dependent quadratic terms in the Lagrangian, you will produce from the vacuum, from the ground state, you will produce a squeeze state in the harmonic oscillator. All right, so here's a review of squeezed and coherent states. So you can define, this is what's called a displacement operator. It's just a definition, and it's a unitary operator that is linked. There's an exponent of something that's linear in the raising and lowering operators. Okay, linear in the raising and A and A. And then you can take this operator and act on the ground state, and there's a parameter alpha which is complex, and so that's the state that you get from taking some arbitrary alpha and acting on the ground state like this. That's called a coherent state. And this state here is an eigenstate of the annihilation operator. So that means that means that there's no fixed number there, because it has a kind of similarity to it. And that's what it is. Now this is okay. So a coherent state. You can also define a different operator. This is called a squeezing operator. And the key difference here is, again, there's some complex coefficient z, written this way, but the key difference is that the exponent now is quadratic in the creation and Navier. Okay. And what I'm calling a displaced squeeze state is the action of you take this ground state, you act on it first by this with some arbitrary z, then you act on it again by some arbitrary alpha. This class of two complex parameter family of states are called displaced squeeze states. And they obey their minimum uncertainty, the wave packet shape, although it fluctuates with squeeze states, but it doesn't really fall apart. It's preserved and it tracks the classical solution.
Then the fluctuations mean, as we were talking about, in some direction for the squeeze states can be big, but what about the displacement?
Here's what it looks like in phase space. So this here is a classical orbit in phase space, and the coherent state is in Schrodinger picture the expectation value, that's in picture 3, is tracking the classical trajectory, and there's an uncertainty which is sort of symmetric in x and p, and that's what you have in units of h bar. It's 1 whereas in a squeeze state, this has the same product, delta x delta p is still 1, so here the uncertainty is very narrow in this direction and much more in the other direction.
And does the Wigner function go negative for squeeze states?
No, it's positive. Yeah. I don't think the Wigner function is a necessary. It's a proposal for how to.
So I knew that for a squeeze state, at least it spreads in one direction, but I thought maybe with the d alpha it becomes a little more like coherent, but that's not the case.
So if I didn't have a d, it would just be somewhere around the origin, and the d allows it to track.
Okay, the classical track, but
it
still
gives it
is spread out. Okay.
Just one comment about the Wigner function is that the Wigner function measures non-Gaussianity.
Yeah.
So these are Gaussian.
What is your intuition of writing this operator S? How do you come up with it, and why not choose the other powers of
right.
writing
Why not go to more
minus 3, 3, 4, 4.
Sure. So you can certainly come up with other powers like that. There's no problem with having an ever larger number of powers. The issue with those other ones is that they don't commute. If you time evolve them with the unperturbed Hamiltonian,
they're not even square integrable. They don't have a finite L2 norm.
Oh, is that true?
Yeah.
Oh, well, that's even more.
That's of course.
This literature is decades old.
Okay, I don't know.
Anish Manohar. Correct. I have the same question.
Great. I didn't think I knew.
We can check it out.
Okay. All right. So these are, so let's see how interactions generate these states. Okay, so starting from the ground state, how do we produce them? So supposing you have a Hamiltonian and you have a time-dependent interaction piece with some small parameter lambda. And so we know that in interaction picture, the state that starts out in the ground state now looks like this, okay? And here you can clearly see that if this interaction Hamiltonian is linear in A and A dagger, this thing looks like the exponent of some linear thing in A, and that would be a coherent state. If, on the other hand, the interaction Hamiltonian is quadratic in annihilation and raising and lowering operators, then this is the exponential of something which will be proportional to a squeeze state. There are also A dagger A terms that can come there in addition to the A squared and A dagger squared. So it's a little more complicated. Okay, so so this is a fun exercise, by the way. A time-dependent interaction Hamiltonian is linear in ladder operators. Okay, so here's an interaction. This is the Lagrangian. This is a harmonic oscillator of the drive with an inhomogeneous term here, classically. And the quantum state turns into is this time. This is actually time order expectation like this. And you can actually work this whole thing out in the full series. And if you do that, and then you take the expectation value of x in this state, you will find the same solution to the classical equation of x that you would get from using the retarded Green's function with this source. So lovely calculation. Okay, so so that explicitly shows that this new state is has some product of that's linear in A's and A daggers. Okay, that's a coherent state. Right. So again, the novel thing that's going to happen, the interesting thing is if this is not linear but quadratic. So first, let's just talk about classically what's the difference between this kind of driving force versus if it's a linear force like this, then if you take the equations of motion, the x drops out, so this becomes an inhomogeneous term on the right-hand side of the wave of the oscillator equation, and so that's just a typical simple, driven oscillator. And as we saw quantum mechanically, that's the coherent state. But what happens if this was x squared? Then this x squared looks like that x squared. So this really looks like a time-dependent frequency together, if I combine. And this is what's called a parametric oscillator. And parametric oscillators, like a swing, have very different properties. Their amplitude grows in time if you push a parametric oscillator. And so we should see interesting things with this that are different from here. So again, here's if I have this f of tx squared like this, I take my x and expand in terms of operators, the Hamiltonian, after the Legendre transform looks like this. And these guys here are going to give me generators of squeezing because there's a time dependent. Okay, so how do we extract the squeezing parameter z or r that I had earlier? Let me just go back, this one here. Okay, so how do I, if I give you a Lagrangian with an f of t like this, and I'm claiming that the answer is a squeeze state, that squeeze state will be the action of the squeezing operator on the ground state. The squeezing operator has a parameter, squeezing parameter. How do I extract the squeezing parameter from this f? Well, it's not so straightforward because of that time-ordered exponential. And so we have to come up with a variety of techniques to recover the squeezing parameter from the Lagrangian.
So how do you prepare these states in lab?
How do you what?
Prepare these states in lab. You they change the change the size of the cavity.
You're asking a theorist? Well, I know that in for electromagnetism, it's quite non-trivial. They have what's called a parametric down conversion of a cavity. I forget what it's called. There's some complicated method. It's actually why in E&M producing squeeze states took a long time. Electromagnetism just resists that. That's so. Yeah. As you'll see in gravity, it's the total opposite. Okay, so there are three methods. I'm not going to dwell on them too much. I'll just give you sort of a upshot. So the most simple one is a direct time evolution. Okay, so here's the operator, and then Shoemaker had a paper in 1986 in which she showed that if you write down, I think she sort of assumed that this operator could be written like this, and then found that consistency with Schrodinger equation meant that these two equations had to hold. They're not easy to solve at all. Okay, so they have to be solved numerically, and certainly cannot be solved for arbitrary f on the right. So here are some numerical solutions, and it's very interesting. So we did the simplest thing possible was we took an f that was just a sinusoid, right? And we said, okay, if you drive it with this, if you have an x squared term whose coefficient is a sinusoid, then what happens to the squeezing parameter? And so capital omega is the driving f, but there's a omega naught, which is the sort of frequency of the oscillator. And here's what happens. If omega is just some random thing, then there is a squeezing parameter. There's R, but it sort of jumps around and doesn't really get off the ground. On the other hand, if at exactly omega equals, capital Omega equals twice omega naught, it starts increasing as a secular increase.
Because the right-hand side produces a resonance now. Right?
Yes, that's right. And this is how it looks for a greater time interval. These other ones are just confined down here, but this one is just going up. So this is the quantum counterpart of what you have in classical mechanics, where there's if you drive at twice the frequency, you get this kind of parametric oscillation.
And if you added a friction, that would taper off?
If you added friction, I think, yeah, of course it will.
We are not talking about driving, right?
We're talking about parametric oscillator.
Yeah.
So it's, the driving would.
What you said would be for driving.
Oh,
No, this is like pumping.
yes. I don't know how it looks if it.
This is pumping of the swing.
Yes.
Take the equation of motion. It has F times X. Take that on the right hand side, treat it as a perturbation. Now X has frequency omega, this has frequency 2 omega.
Okay.
So you get a frequency omega.
Effectively, kind of.
Effectively, it needs a perturbation.
Yeah, probably. Yeah.
And, oftentimes, for example, in cosmology or whatever, you have a time-dependent situation, and then the time dependence ends, say in some asymptotic way.
Right.
And then you have an oscillator with some frequency to begin and maybe
Yes.
some to end. But if you began with the ground state, you end in a squeeze. In that case, perhaps just in terms of integrals of f or something, there might be.
Yes, there is.
Okay.
We'll get. So yeah. So I'm going to speed up here because this is a 1 hour talk, right?
No, it's not. It's not.
Oh, really?
It's like a 2 hour talk.
Is it?
2 hours and a half.
It can be 2 hours and a half. Yeah,
Okay,
exactly.
okay.
1:30.
Then I don't need to.
1:30.
Okay. So good. So the upshot here is that any dependent, it's Russian style. So, okay, good. Any time dependence produces some squeezing, but this Fourier component. So
Other multiples also.
that's a very interesting question. So the parametric oscillator, classical parametric oscillator, does have overtones also where the multiples also go. I wasn't able to find this numerically in the quantum picture. So I don't know if I made a mistake or something, but I didn't see the overtones help us.
But classically, there are.
Classically there. Okay, here's another method. So supposing you just solve this equation, because remember the f of t's can be combined into effectively a time-dependent frequency. If you could solve this equation, which is a linear ODE, okay, then from that you can basically take those solutions and compare it with the solutions that you would have had for the the sines and cosines that you would have for the free oscillator, and write them as a sort of Bogoliubov transformation, and then indeed you find that R is very simply abstracted as arcsinc of the beta. So if there's a non-zero beta, you will produce squeezing. And think about how many circumstances you have in quantum field theory and curved spacetime, or where there's a non-zero beta, right? Every basically time-dependent cosmology, Hawking radiation, et cetera, is always producing this. In all those cases, you're going to get squeezing, right? So if we were fortunate enough to be able to solve this equation, then this is a much easier way than solving that horrible nonlinear coupled equations.
Beta is related to f in something nice.
Beta is, yes, because, well, beta is related to the coefficient that you would get from expressing the solution of this equation in the original equation. So, yeah. Okay, there's a third method called Magnus expansion. So if you have this sort of unitary operator, you can write this, and if there's a small parameter lambda, you can take this thing and write it as an exponential of powers of lambda. Instead of writing it as powers of lambda just as a perturbation series, you can write the perturbation series inside the exponential. Okay, so this is called the Magnus expansion. And the first order term, first order here will just be e to the minus h int, and so indeed omega 1 is h int, and then omega 2 is like this, and if you expand it, you're going to get This is the Dyson series coming out.
So
Now-
this is some form of the Dyson series, some.
Yeah, this is a way of regrouping the Dyson series. Yeah. So Dyson series, the lambda expansion is, if you already expanded in lambda, but now you imagine that they're all in an exponential. So with the higher ones, they're going to start mixing up material.
So this is good when there are very high frequency modes and something.
This is good when there's a small parameter lambda, because this gives you a perturbative way of calculating. So you want to estimate u, but because of this time ordered product, that's not so easy. But if you could write it like this and restrict to whatever power of lambda, then you get so. Now the good news for quadratic h, right, is that if they're quadratic h and quadratic h here, the commutator is also a quadratic h. So these guys form an SU11 algebra. And in fact, you can write them in terms of a usual L plus L minus sigma. And then you can say, oh, I've got an exponent of a bunch of these operators. And so since BCH is representation independent, you can do this. You can exponentiate it using BCH. You find this. And there's a way to calculate R from this. So in other words, given an interaction Hamiltonian, you can, to whatever order you want in lambda, you can write down what this looks like in terms of powers of A's and A daggers, re-express those, which will all be quadratic, re-express those in some linear combination of L plus L minus L naught. That will give you these coefficients C plus C minus C naught, and then you're squeezing parameters.
So where is the time dependence of the interaction?
These coefficients are all time dependent.
C's.
Yeah, C's, D's. Yeah.
So when the time dependence goes to zero, the derivative vanishes, you should not get any squeezing, right?
Right. Then probably this commutator is zero. Right, yeah.
This SU1,1 makes it seem that it might even work for a general lambda, but that's probably doing. I mean, just if it's quadratic, it's just so simple. The commutator is quadratic, the second commutator, etc. Think a little resum. Okay, anyway.
Yeah.
It's sort of
You're saying not order by order.
not order by order. That there's so much structure that okay.
So this is also this is exact, and then you can because it's it's not really exact, because to know what these coefficients are, you're presumably stopping at some finite line. Okay, and then of course field theory. I'm just going to pause for a second. If you take this, you can write the field in terms of modes, and again, if there's a time-dependent piece here, that's going. This again, just every field right then this sum of harmonic oscillators. So it's no surprise that this turns into the same story, but the sum over harmonic oscillators.
And this continues to be true, that in order to see real squeezing, you need this multiple.
Yes.
Even with that exact answer, one can see that that was for general time dependence, right? For the previous
Sorry,
slide.
the question is, would you see
There was some resonance type
Yes.
behavior, right?
Yes.
Where the
when it's too well? All right, we'll get to what happens if there's. I skipped
in
this.
this previous slide, you had some exact which did not really care about how the time dependence looks.
Yes. Yeah.
So there, if you kind of specialize to that case, you see
Yes.
that for when those are not multiples, there is some interference, but
And okay, I cut that slide here, but one of the things that is more interesting is that this function is not just f of t, but f of t and x. Then if you take this Fourier transform, it mixes up all the k's and k primes. Okay, and then you get actually quite interesting behavior, that the sum of those k's and k primes has to be omega naught, right, or twice omega naught. So you get this combination, what's called combination resonance. Okay, so gravity. That was a big step from the harmonic oscillator to gravity, but it's just field theory here. So unlike electrodynamics, classical sources in gravity, as we'll immediately see, naturally produce squeeze states. So what's the difference? So the structural difference between gravity and electrodynamics is very simple. The electrodynamic action can only support a term like JA. You can't write JA squared because that's not gauge invariant. Okay, and once you expand A in terms of creation and annihilation operators, this is going to be linear, right? So you need something like this to get quadratic, but you can't because of the application. So this will inevitably produce coherent states. There's the question asked earlier: parametric down conversion and nonlinear crystal, whatever that means. And so this is what you have to do to get. You essentially have to force this to be effectively nonlinear. Now, in gravity, by contrast, we're expanding in powers of h, and all of these things, both the inverse metric and the root g, have all kinds of powers of h. So automatically, you're going to get quadratic and also cubic and other terms. So if there's any time dependence in anything here, okay, that looks the quadratic order like it's going to produce these states.
But still, you will get a linear term, right?
Yes.
And sorry, maybe you're going to come to this, but you might just think by the time you put in factors of m prime, the linear term will typically dominate the quadratic because fluctuations are small and suppressed. So will it be that you produce primarily coherent states with a bit of squeezing?
So the question of how big the squeezing parameter is, that's the next game in town. There's no requirement that it has to be small. We're not doing some expansion, and as we saw, it can grow in time. So that gives you the hope that you just find some phenomenon and just wait, and it'll become more and more squeezed, while still behaving at the expectation value the same. So the expectation value would be that of a classical solution of Einstein's equations, but it has some feature that's more and more important. That almost works.
So as you're comparing the electrons with the gravity, so Jimmy is the source and Jimmy is the field.
Jimmy would be some source, which would be hopefully time dependent. Right. If you try to take a time dependent source for the field A, we're expanding A in terms of creation and annihilation operators, and in terms of modes. Each one of those modes is a harmonic oscillator. Right. So there's a whole bunch of modes, harmonic oscillators, and then there's some interaction Hamiltonian created from here. This is the interaction Lagrangian here, but that can only be linear.
Right, but here in the gravity, what are you talking about? So what is the source times?
So in gravity, there are two kinds of sources. There could be a matter source, but the geometry itself can be a source. I should have written down matter source.
So there should be some distinction between source and the field. Right? The field is the metric, then what is the source?
So we're doing perturbative gravity. So we have a background field, and then we have the H. So if the background field has time dependence, then the H will see that background field as a time dependent source. The next slide will be that. So
what about Young's theory?
Sorry?
Young's theory?
I did, well, yeah, you would have the same thing. It'll very naturally produce squeezing. Theories like that. I briefly thought about also things like axions coupled to electromagnetic. If you have an axionic coupling to E and M, then time dependence of the axion can actually give you squeezing. There should be others.
As Harshit said at the beginning, in electromagnetism, you should just oscillate the size of the cavity. That would also give you squeezing. Because omega set by n by L.
Yes, yeah.
You just oscillate L.
Yeah.
That would give you.
I think that's actually what they do. Okay. But I don't know how to represent that in. You're varying the boundary conditions.
Yeah, right.
Right. So it's a bit tricky to write this the way we do. So, but yeah, that's probably another class of ways to do it. Time dependent boundary conditions.
So I guess in gravity you don't have to do anything to get that.
Yes. Right? Yeah. Gravity is just automatic. Yeah.
One question about the structure. So even if I couple, say scalar matter, maybe there's an a squared term, right? There's an e squared, a squared term.
Yes.
So I see linear quadratic in E and M, and I see linear quadratic in Q higher in gravity. So what is?
Sorry, where does the a squared come from?
It's just d mu phi minus
a mu
phi squared.
Yeah, so I think that would be I mean, we do know there's squeezed light, right? So it's not, but I think if just this kind of, where is it? This kind of term does not do the job, but maybe I think.
Sure.
So, and in gravity, I mean, let's say in some situation, the cavity itself is automatically dynamical.
That's right.
Right. So this suggests that basically to produce significant squeezing, you need a significant fractional variation in the geometry.
I don't know, because it could also just go on for a while.
There's
also in the, so yeah.
Sorry, what is the extra ingredient in gravity just making it so easy? I guess
The fact that that just every action, almost everything you write with time dependence, everything you write has nonlinear pieces with h, and if any of those are, if any of these blue terms, I don't know if you can see them, 5 blue terms and this red term, they all have an h outside, so these are quadratic. If any of this is time dependent, you have squeezing.
And the depends also from background.
It can come from 2 sources. It can come from a background, or it can come from time-dependent matter. I'll give you examples. So there are 2 sources. Curvature couplings. If there's a time-dependent background, like in cosmology, okay, then you will get squeezing from the geometry. If there's a time-dependent source, then you will get squeezing from matter.
Okay, sorry, but there will be a linear term, right? Suppose instead of the source J, you had matter in gravity.
Yeah.
It would couple linearly to
Yes.
the gravitron. So there would be that effect. But
Yes. Yeah. So the linear one is going to give you the solution of that will give you behavior of H. H will be source, will be box H equals T. But so that's the classical solution, and that's the expectation value that you'll get. But the variance will be dependent on the squeezing.
This is like the omega naught is 0, right?
Why? No.
The massless.
These are all going to be expanded in modes. So for any particular mode, there's a given omega naught.
Yeah.
Okay, so here's.
So I just have a concrete model in mind. Suppose I had a black hole, a short-shaped black hole,
Right.
and I start throwing in some mode with some angular momentum so that it can radiate that angular momentum in a sinusoidal manner. Then I could presumably solve this problem.
Yeah.
And there'll be some sinusoidal radiation of gravitons in that L mode, which will start squeezing, right?
Yeah.
So we could set up a toy model. That's quite easy.
Yeah, there's a simpler toy model than that, but something like that. Yeah. So I'll give you 3 examples. The first example is FRW. Okay. So yeah, that's right. Anything that has a beta will give you squeezing. So here's FRW. I've taken the metric, written it so. This is the action to second order after I've imposed some gate choices here, Lorentz gate, TT gate, and so on. And so this is what I get. Okay, so I get this is my usual piece, but then I also have a Riemann piece here, and because there's a H times Riemann, this is like and this Riemann is time dependent. This is a time dependent. If once I expand this in modes, this is going to be a time dependent. Indeed, I've done that next. I've taken my H, I've expanded in terms of polarizations and modes. Here's some polarization tensors. Here's the EDI-KX. Here's the amplitude, K-dependent amplitude. So each one of these is like a harmonic oscillator. This is complex. These are real. These are complex. And so I can take this one and write it in terms of real and imaginary parts. And then putting all of this decomposition into here, okay, sure enough, I get now eta is like time here. I have a Lagrangian that looks like this. I have a sum over polarizations and K's as usual. I've got now these X's. These are my oscillators. I've got 2 sets of harmonic oscillators, one for the real and one for the imaginary part. And you can see like 1/2 x dot squared, and then here's x squared squared. But this piece here has a time dependence. This is the omega naught squared part, which depends on case.
So I'll give you a basic question. Can you have a situation where your uncertainty reduces with time?
Reduces from coherent.
Since we're dealing with time-dependent situations, can you have a situation where you have some Hamiltonian and then you start with some state and your uncertainty reduces?
So in this case, my initial state is I'm just going to take it to be the ground state, the vacuum state. So that's a coherent state, it's a minimum uncertainty state. Now, when I squeeze it, the uncertainty is going to get reduced in one direction and increase in another direction. But you can't reduce it in both directions because it's already a minimum uncertainty state.
I thought the uncertainty is saturated in both the directions, right?
In the coherent, well, I don't know what that means. So uncertainty is a product.
Oh, you mean the phase space? Delta x times delta p is.
Yeah.
Okay.
Delta x delta p is 1/2 h bar, right? But that doesn't mean that delta x has to be anything or delta p has to be.
Yeah, but I was asking, maybe you start with a state where the bound is saturated. Delta x delta p is. Sorry, you start with something which has more uncertainty and it becomes saturated.
Oh, I see. So you start with something that's not the ground state.
That's not classical in some sense, and you reach classicality.
That's a good question. I don't know that. Yeah. Okay. So anyway, here's the F. All right. And for each mode, omega naught is this. Okay. So all modes are parametric. And then if you plot this, it's easiest to do it for de Sitter space, where F is this nice 1/8² and here's the mode equation. You can use a variety of techniques to get R, but just the numerical one is simple enough, and you can see that after some initial thing, it's basically there's a linear growth in R, and it's going 0 to some decent values here.
What was the R again?
R is the squeezing parameter.
Squeezing parameter.
So Z is the complex squeezing parameter. R is the absolute parameter. Okay.
This is the usual calculation, right? For in the case of inflation.
So this exactly matches Richter, 1975. So he's saying that the gravitational modes that you get from inflation, it's true for all things, it's not just gravity, will be our squeeze states. And so they're of order, 100 if for things that left after inflation. Okay. Here's a kind of silly example. Kazner, which is some random geometry, it's tractable but totally made up geometry like this. And it has, I think it's vacuum if these conditions are met. We have some pressure, some coefficients in different directions. It's totally it's homogeneous but not isotropic. And with this particular condition, I think it has maybe it's vacuum. And so then the equation of motion becomes this, that can be solved exactly, and you can use Bogoliubov methods to see what R is. And you find again that as time goes, there's oscillation of the squeezing parameter that it again grows linearly. So this is another example of a vacuum space-time where the time-dependent potential comes purely from the Riemann tensor. There's some Riemann tensor, it's vacuum, but that's sourcing because gravity is self-interacting.
But you just say once more, what's R?
Okay, so R is very important. R is the absolute value of the squeezing parameter. So we're interested in ultimately squeezing operator. It's the magnitude of Z. Yeah, there's some phase which just simply tells you what is being, how in phase space I'm squeezing, whether I'm squeezing in the x direction or p. That's controlled by phi, I think, but the magnitude is R. So that's what we are after. So given some F, given some Lagrangian, what is a high power? Okay, last example, and this one is a real example, squeezing from matter. So for a scalar field, we now should hopefully fully absorb that you need quadratic couplings to time-dependent coefficients for quadratic terms in the Lagrangian to get squeezing. But so for a scalar field, you would need a coupling like this, J phi squared. Normally we just write J phi. Okay, so this is not the usual kind of coupling. Could write it, certainly if it is coupled to some other field. Okay, for the cubic coupling, power type coupling to another field, that would end up being this. In electrodynamics, such a term is forbidden by gauge invariance. You can't have something a squared, though, of course, there's the other example you have. But in gravity, as we saw with our angles. So now let's just take a very simple case where I'm going to look in Minkowski space, okay, for and there's going to be a object, a particle with some trajectory x, okay, in Minkowski space, and here's the action, and I'm going to see how does this motion of this particle produce squeezing of the gravitational field. So I take my g, which is eta plus h, right, because it's Minkowski space plus fluctuations, and I expand this to second order in h, and this is what I get. Okay, so this is manifestly quadratic in h, and the prefactor here is this x dot a, x dot b, x dot c, x dot d over this. If there's time dependence here, which inevitably there is, okay, then you will get squeezing. So let's see a very non-made up example of that, which is a binary black hole, particle orbiting another particle. So this you can think of as the extreme mass ratio in a spiral, where we're considering a background which is fixed, black hole background.
So you don't need acceleration, right? Or just
yes.
a x dot. No, I mean the previous slide, it just everything was dot.
So this is a very subtle point. So here it looks like you would get it with just the x dot.
Yeah.
But there's a slight there's an assumption. If it was only x dot and no acceleration, that would mean that it would be like that forever. But our assumption that there was,
right?
yeah, our assumption was that at some time t equals 0, it's the vacuum state. So that's inconsistent with purely x dot. Okay, so there's a subtle point that was actually quite complete. So we need to have acceleration because we're going to take a starting point that it's vacuum and then evolve from there and get it squeezed. So here's the metric. There's a Newtonian potential here. Here's the trajectory. It's just going around in a circle, cosine omega t, sine omega t. Okay, and so then we're going to assume that m is much less than m. There's actually an example of something that was like this. Funnily enough, most of the black hole cases that LIGO has seen are black holes that have similar masses. But there was one example, which is a neutron star black hole event, where Q was 0.009. I think Q is the ratio of these masses. So one was much heavier.
That aspect is not really essential, right? That one is lighter than the other.
Well, it's not essential, but this calculation would be much more complicated if both black holes were. Here I can regard the background as stat.
But as far as producing this squeezing is concerned,
in principle, no, but in practice, I don't know how to control the calculation.
Yeah.
Geometry is changing like that.
But if there are similar masses, can you not do the analysis of reduced mass or something that is always being classified?
Yeah, so this is another thing I learned. Reduced mass doesn't really work if it doesn't even work if you take two relativistic particles, there's no reduced mass picture. Just kind of surprising. Right. Okay. So this reduced mass reduction only works if it's non-relativistic to begin with, which turns out to mean small phi, which turns out to mean close to 2 million. So, okay. So what happens?
I'm waiting to ask you about the M Plancks in R proportional to T.
Here they come. Everything is going to be okay
Because it's got to be suppressed.
This is the real thing.
Yeah.
I have all the Q's and pi's and everything.
Right.
Okay. So this is not Kazner anymore. Right? So the interaction Hamiltonian is expanded like this. Okay, let's just understand why there's this horrible mess. First of all, we're just taking this Lagrangian, okay, which to second order in H, so we can actually throw away the bottom. And then we're taking the Legendre transform to get the interaction term. We're going to plug in X. I'm just going on without any time constraints.
I mean, there is, of course, also just the linear term, right?
Yes.
The source.
Yeah.
But In addition, the quadratic will do.
That's right. The linear term will give you the usual
Okay.
motion. Okay, so in the language of so the linear term will give you the displacement part, and the quadratic will give you the squeezing.
Yeah.
So there's a displaced squeezing thing. So the linear term will track the classical motion, and the squeezing will give you the noise. Okay. All right. So here's my. I've taken both those h's since it's quadratic and Fourier transform them. That's why they're 2k integrals. They're the sum over s's and s primes. Here are all those x's that were there before. There's the polarization tensors because they're epsilon. They're taking Fourier transforms. I've expanded the h's in creation and annihilation operators, and this is the whole thing. Okay. There's your beloved M plan. Okay. So, and then this is a mess, but there's a small coefficient here, which I think I've lost somewhere, but it's a phi, the Newtonian potential here, which is somewhere, and that's small. So I can therefore approximate this in terms of some Magnus expansion thing where we know how to solve. So here's my squeezing parameter, okay, and it turns out to be all of this. Okay. All right, so let's just see what this looks like.
Can I just say one small thing?
Yeah.
I might have. So 1 over n Planck square is of course g Newton, and just even the linear, response would be suppressed by g Newton, right? So I might have thought the squeezing was further suppressed because it's a 2-photon effect. I mean, a 2 graviton. But I'm a bit surprised it's even as big as it is somehow. Maybe I'm missing something, but because if I put in,
You're asking in finite diagram language.
Yeah.
Why is this?
I mean, I would have just thought that the linear, if I just think of it as a classical effect, that should be g Newton times the mass. Now, the squeezing is a quantum, so there's an additional suppression. This is how I was thinking. But I seem to be wrong. Huh?
At the level of the Gaussian wave functions, again, the quadratic, it's a minus h squared.
Yeah, I was thinking graviton fluctuation should be down. Somehow I'm surprised. Okay.
Yeah, just to work Sandeep's thing again. Is it right that because you're producing radiation? No, it's not that, right? The squeezing is happening directly because of the matter, not because of the radiation produced by the matter.
Yeah.
I see. So
Yes. I guess we need that.
yeah,
It's not we're not seeing some kind of back reaction of the radiation. It's just, in fact, a nice example is there can be examples in which there's no linear term and there's only quadratic term, in which case there's no classical gravitational radiation at all. And you have a state that is that has much more fluctuations than the vacuum state.
but the graviton that's being radiated is now is squeezed.
Yes. But you can have something where there's no graviton being radiated, so the expectation value is 0, but variance is not 0.
Okay, even where, yes, so this is more interesting. I understand.
So
Bigger effect than I might have liked.
So here's what a kind of common integral that keeps coming up is this. All of these x's here are sines and cosines, so we insert them into this exponential here, and we basically get this kind of thing. And interestingly, okay, so then there's some expansion of this in terms of Bessel functions, and here's something very nice that happens automatically. If you look at this piece here, you can see that when can be a pole when these two things, when this denominator goes to 0. And this expression here then gives you t. If this is appearing in the denominator, this gives you t. And so for the harmonic oscillator, we saw that you would get linear growth in time if the driving terms where the driving term, in this case omega, was twice the omega naughts. Okay, here the omega naughts don't have to be the same. They can be 1 omega k, 1 omega k prime. They can combine to give you this omega. So this is called combination resonance. And so enough that the sum of two graviton frequencies has to be an integer multiple of the orbital frequency. So,
Sorry, just to process what you said earlier. So the displacement term, of course, might not be comparing apples and apples, but the displacement term is also g Newton times m, right?
Yeah.
And the squeezing term is also kind of comparable, right? I'm just asking. It seemed from what you said.
So this is, well, it's not quite. So this is what we get. So yeah, no, that's, sorry, what is m Planck squared versus
I mean,
g Newton is m Planck squared.
so this is right. It seems just g Newton suppressed, right?
Yeah.
So, okay, and sorry, just to ask you, if it had been the case that the displacement term was much bigger, the system would have had a bit of squeezing perhaps, but just behaved classically, right? Or is that even not true?
It's always behaving classically.
No, it's behaving classically, but I guess the fluctuations are just governed by R, right?
Yes. Yeah.
Independent, yeah. Okay.
So, yeah. Well, so the bottom line, we can calculate all these polarizations, and we really did it for the full thing here. And we found that the kinds of things we get for different polarization, different case, they all have this kind of factor in front, and there's linear growth in time.
So regarding this linear growth, this is something that continues to infinity. This growing.
I wish.
We do see there's a breakdown, right? Something.
So unfortunately, so we were very excited. Linear growth in time. We just wait. But growth in t is not unbounded because the orbit itself is decaying by emitting gravity. So there's a finite number of orbits that it does before it goes away. And so because of that, you can calculate what's the maximum. And we find that it's about it's about 1/3. Because so R becomes 1/3. Now 1/3 is not a big number, but it's not 10 to the minus 5 or 10 to the minus 30 or anything like this. So it's not, doesn't have the smell of quantum gravity but it doesn't really help us for what we're going to do next. So the binaries in the inspired phase squeeze, but only by a little bit. But the formalism is general. So, I mean, here we looked at the in-spiral phase, which is probably the least dramatic part of the merger. It has the advantage that it goes on for a long time, so that's why the T could have increased. But also, it's the most classical part of the orbit, right? And maybe as we plunge in, maybe something different will happen. We're trying to think about how to model that, like maybe a fall into the horizon.
Time to ask you this question, although I should wait. Yeah, people have thought a lot, as you know, about parametric resonances in inflation.
Yes.
But I mostly what I know is for scalar perturbations. And natural question, given what you're saying, is whether we could do parametric resonance in some way for the tensor. Okay,
that's what Grisham did.
That's what he did?
That is what it did.
No, I thought that was the standard. That's not the standard. This is the standard calculation of how tensor modes are produced, which don't use a version of inflation which has any kind of parametric.
Right, but what he finds is that if he writes it as a quantum theory, that it looks like a squeeze state with growing.
It looks like a squeeze state, but I was wondering whether you could set up a version of where your frequencies are matched, to get an enhancement.
Yeah.
And people tried that for the scalar mode quite a lot. I was just, your talk is.
There are so many examples. Maybe they're axion clouds. Who knows? Anything where some frequencies are matched, we would get something.
Sorry, repeat your question, Sandeep. So tensor mode comes from a different origin for that. I mean, Einstein is Lagrangian, right?
Yeah, just Einstein's Lagrangian. As Maulik was saying, these gravitons, which are moving in the time-dependent sitter like diagram. Because of the time dependence, your masses or whatever, the frequency is time. So incorrect.
Right. No, but you're isolating tensor mode versus scalar mode.
Oh, right. No, just spin 2. The spin 2 part.
No, but that is supposed to be some sort of a better signal of something than scalar mode, right? So I was trying to.
Oh, no, just for graviton, a graviton quantum state. That's why I said.
Okay, establishing spin 2 versus spin 0.
Yeah. Since the talk is about quantum mechanics.
I'm a bit about the perturbation theory. So you're taking only the quadratic terms here.
Yes.
But when you keep squeezing a mode, you're also increasing the energy of that. Because I mean, you're saturating the uncertainty system. Delta X, delta P is.
I don't think you're
But
increasing.
P square itself is getting large if you're squeezing in this way.
I mean, its fluctuations can be large. Right.
P square is.
Oh, yeah.
That's fluctuation.
Yeah.
Yeah, I mean, P minus P naught square. Yeah, which is also large, right?
I don't know if P naught is large.
You can go in a plane in which, sorry, not a plane, but I mean, you would have a mode which has zero momentum.
Yeah.
Right? And, it has large fluctuation in it.
Right.
And that will give, I mean, the energy of that mode will be large.
I guess that's true.
So I'm not sure if you can ignore higher order terms. I mean, at what time the quantity is not clear from this.
Yeah. So again,
Sorry, I missed that. You mean the cubic and so on? Directions?
the bigger question, I'll just reformulate your question, is that Einstein gravity produces these quadratic terms, but actually gives us also the other stuff too, right? And we have so far just neglected that. And there is a question about how, if we're treating this term, what's the effect of that? So I don't know.
Well, there's something intuitively something funny, which is probably my misunderstanding. I mean, if you had a harmonic oscillator and you keep doing this F, because the F is acting where the harmonic oscillator is,
yes,
I can imagine that it builds up. But here in this case, this guy is emitting the graviton and then it just goes.
Yeah.
So how can the squeezing build up once it's gone?
It doesn't. Once it's gone, it's no more build.
So then
the finite builds up. That's why the answer is only about 0.1, 0.3.
No, but I mean, that finite thing you said was from the inspiral, right? The decay of the orbit.
Yeah.
But I was thinking the time scale would be just set by how long it takes for the graviton to move away from where you are, which is very small.
From the graviton to move away from...
To escape from where? It's been radiated, it's gone far away.
Yeah.
Now that this is happening, why does it care?
I don't know if we should think about it as the graviton taking away the squeezing, if that's what you mean.
I mean, we're looking at the squeezing of the graviton, right?
Yeah, but there's a state.
Mm-hmm.
And I think it might be helpful to not think that there's anything radiated at all. And then you can imagine that state becomes more and more squeezed.
Right, so that's the harmonic oscillator picture, and that seems very reasonable.
Yeah.
But I was trying to think of it from the point of view of locality. Maybe it's because you're working at a particular case, so it's all over space.
Yes, I mean, that's all. I am doing it mode by mode. Yeah, so that's maybe...
Yeah.
Is that the answer?
But another way would be gravitational waves also kind of going along with this, right?
But I was thinking physically, I do something for a while, that creates a gravitational wave that has gone far away. Once it's gone, what this is doing now no longer.
No, I'm thinking of graviton versus gravitational wave as separate. I mean, gravitational wave is producing the background for it.
So I don't think we should think about the thing as necessarily noise inside the gravitational. It's not like jitters on the wave necessarily. However, the thing that usually produces the wave is the same thing that produces the squeezing. So in that sense...
But it's producing squeezing of the radiated wave, right? So once the radiated wave has gone, why does this have to matter?
As you said, right, it's HK. It's a K, a momentum, not a position.
Yeah, so but in a real situation, this starts happening at some time.
Yeah.
And then that produces some radiation that I could measure now. I don't have to wait forever. So
there's also local gravity, right? A local gravitational field near the particle, which is
yes,
that cannot squeeze.
but that's not what we're measuring, right? We're measuring the squeezing of the gravity of the radiated gravity.
We just put it another way. I mean, suppose I build an example of an antenna which radiates with a linear term. As radiating photons or whatever frequency omega, they come out roughly on times of 1 over omega.
Yeah.
Now, how do you get a build up the squeezing? Each 1 over omega you emit photon as the dipole. So it's a bit strange to me.
So should we not distinguish the classical background wave versus...
Yeah, I'm not sharing this intuition about the classical gravitational field taking away.
No, sorry, maybe I'm just misunderstanding, but I thought what your conclusion is that the radiated gravitons are squeezed, right?
I don't know.
As opposed to the classical radiation.
There's only quantum.
There's only, so I just want to call, so I want to say there's a state,
Yeah.
and that state at the end of the process is squeezed in certain modes.
Right. But let's say I'm interested for measurements, for something observational, which I'm sure you are.
Yeah.
Okay. You're going to observe this for the radiated gravitons, right?
Yeah, I guess. Right. So
Maybe what you want to do is track a wave packet.
I track a wave packet, and then once you do that, it feels to me what's relevant is the timescale for the escape rate.
Yeah, I mean, the frequency, to put it another way, the frequency with which the wave of the graviton is emitted, right? That's much smaller than the total in spiral time. Right?
yes.
We'd be willing to give that much time, right? Of order the frequency.
Yeah.
But to given the entire
It's the orbit
time,
the frequency is the orbit.
is the orbit time.
Yeah.
But this is much bigger, right? Because
You just
I don't know
wait
how many it goes around.
It's 1 over Newton times constant time.
So I think, okay, so let me understand. So you're saying that intuitively, how do we, once it starts radiating classical gravitational waves, why is it getting more squeezed, whereas each one is?
Once
Is that
it's
what
gone.
you're asking?
Yeah.
Well, I don't know how to interpret the physics. This is the
No, so it's a clear calculation.
Yeah.
But I was wondering, as Onkar was, that if we now take, is it very sensitive to the fact that you're really working with a pure wave? Then you take an appropriate superposition with cases, and that gives you another different behavior, because that should sense your canon.
But I didn't take it. So I did what we normally would do in calculating gravitational waves in any textbook on GR. The standard case for the in-spiral phase is you just take a particle in a Minkowski background, and this is how you calculate. This is so you provide the trajectory.
And so you're saying a given K mode
Yeah.
comes out squeezed, right?
Yes.
Now I'm wondering whether if we now take wave packets of this to model what we actually see, that sort of
Sorry, when we try to get the classical waveform of this, there's no further modeling. You just provide this trajectory, and that's the source of the gravitational waves.
absolutely.
So we don't then say, now let's assume something about the waveform. This is the source. So I don't understand where there's room for
Yeah, but the curtain. Okay. What is strange is that this thing is building up over times after it's left. That doesn't happen classically, right? If the classical wave is gone, it's just free strings. And so there's nothing left to do. What's strange here
that's
is
kind of a locality argument.
Yeah, locality.
But I don't know if that's the right. Let's see.
No, I mean, it's probably
an individual K mode, which is everywhere.
That's the problem, right? Now, but physics is actually local. So
yeah. But to put it another way, let's say the spiral would come for a long time, and you're measuring a souped-up LIGO and trying to see whether it's squeezed, right? Now these waves come, over a period of time for the full in spiral, but at each instant you're looking, you're going to see the total build-up of it. Seems.
So I'm sure this is stupid. I mean, just go, yeah. And it's probably stupid.
No, it's not. I mean, it's tricky to connect all the things we're actually measuring with these theoretical problems, and but yeah. So I'm just not completely on board with the intuition that there's something that the gravitational wave is. That the squeezing is sort of moving along with the gravitational wave and being subsequent. I don't.
But let me just say this: suppose I have this, I make this do 10 rounds, and then I blast it. There's a nuclear bomb that finishes the planet. The radiation that's come out after that doesn't care, right?
Let's take the opposite extreme. Supposing nothing comes out classically,
Yeah.
Okay. There's still something building up. Yeah. How does that fit in with your picture that something that
No, whether classically or not. So there is some wave function for what comes out. But once it's gone far away, it doesn't care what's happening later on. Whether classically, I'm not saying classically. I'm saying just look at
I didn't understand it, but I thought the thing that is going on is that I am in a lab here and I'm seeing some gravitational radiation in the sense of, the background being, oscillating, the classical geometry oscillating. And then on top of that, because that then serve as the time-dependent source for the gravitons that I would potentially see in this lab, right? I thought what these gravitational waves are doing is providing that time-dependent background.
No, that's
The problem is that there would be much
Newton constant
squared. Okay.
This is
That's
just the motion
but
itself.
for this phenomenon, this is correct then, right? If I can see
Yes.
to the next order, I thought that is what was going on.
No,
So that's not.
that's not.
So then I'm also there.
This is just the motion itself. That's provided. This is the matter part of the action. But maybe what it is that the squeezing builds up. So if you look at the okay, let's say there's a wave packet that's made up of. So I'm examining the wave packet as a function of time, and let's say it goes on for a few days, right? And so the beginning, I might see less squeezing, and as it builds up, I might see more squeezing. That's possible
That's possible. I mean, once the stuff that's been radiated
Later.
because the stuff that's radiated later is not in a state which is the vacuum state anymore, right?
But even that is
seems strange.
Yeah, because it
seems
happens over
strange.
one radiation.
Yeah. Because the time scale is that's why this antenna example is clearer in my mind. If the antenna is going to be radiating, you just have that much time, the oscillation time.
Oh wait.
You forget everything.
So the subsequent radiation, is a displacement term that is happening for a state that is now more squeezed than so it started out with a vacuum state, right? It does a few rounds. Let's say it does one round of this, emits some gravity, but now it's not. The next one is not in the vacuum state. It's in a somewhat squeezed state. So maybe when that one is radiated,
Once you say in the language of harmonic oscillator, sounds totally clear. Because everything's there. The strange thing is the locality.
Yeah. That's why in cosmology it would be fine, the R, because that's like the okay. Anyway,
all right. Well, I clearly have gaps in my understanding of this.
it's very interesting.
All right. So finally, this was the last part of my talk. I'll speed through this a bit because this is the oldest part of it. But the whole motivation behind all of this is there's experimental effects that may be measurable. So this was the signatures of quantum gravity. So let's just quickly go over what this is. First of all, we never measured the metric directly, right? It's not gauge invariant. And everything we do about gravity, all measurements are actually indirect measurements. We're measuring something falling, right? So we're measuring geodesic, we're looking at geodesic motion, whether it's Mercury's geodesic motion, whether it's galaxies' geodesic motion, light, or the mirrors of an interferometer, which are actually also more or less geodesics. Certainly in LISA they would be. And the natural gauge invariant object is actually is a geodesic deviation. That's gauge invariant. So this is what we normally see. This is the equation, the geodesic deviation equation, where R is basically an H around the Minkowski space. Okay? This is what LIGO measures, right? So this is xi, it's the separation, the geodesic separation. So there are two mirrors. Okay, let's say it's LISA, they're falling in space. And there's some geodesic deviation xi. These are two geodesics, that's the deviation xi. As a wave goes through, this thing fluctuates in accordance with this equation. Okay, that's what we measure. We measure that the whole point of the laser is to measure that distance effectively. So this is what we measure. And the question is, this is all classical, but what is the quantum analog of this when this space-time metric is regarded as quantized, as a quantum field? And this is a series of papers that I wrote with Frank and my former postdoc, George Zahariadeh, faculty in Poland. Here's what we found. We start from first principles. We tried to first guess what the answer was, and we just got completely confused. Monday, Wednesday, and Fridays, we get one answer. And so finally, so let's just do it. And so this is the as first principles as you can possibly get. Here's the action for gravity coupled to two particles, right? And then we can use TT gauge, put one of them at the origin. Okay, we can just choose our coordinates. So one of them is at the origin. Look at the position of the other one. That's now gauge invariant because it's relative to the first one. Use TT gauge. This is expanded around flat space. And then expand in terms of modes, take the non-relativistic limit, and so on and so on. This is what we get. When you do all that, you get a Lagrangian for xi is the separation between the two particles. And that looks nice. 1/2 m xi dot squared. This is what you would get if you had two particles expanded in their difference, kinetic term of difference. Q is the amplitude of one of the modes of this harmonic of the gravitational waves. Okay, so there's a subscript omega for each, or k for each of these modes, which are dropped. So that's again the usual story that each one of these each one of these modes for free field is a bunch of harmonic oscillators. And then there's this interaction. And the interaction that you get comes from expanding this, and you get, after some integration by parts, I think, you get this kind of stuff. Now, the double derivatives is because this is GR, and so there are always two derivatives, so this is what we get. So this Lagrangian is almost as simple as it can get. You have a free particle and a simple harmonic oscillator with a derivatively coupled Yukawa term. Okay? And because it's quadratic in both Q and in xi, in principle, the path integral can be done exactly, not just perturbative. So there's a whole technique to doing this, which was developed by Feynman and Vernon, where we're going to integrate out, so we're going to take a double path integral. We're going to integrate out gravity, which means integrating out the Q. We're going to get an effective double path integrals for the xi.
Which will depend on the Q.
Which will depend on the state of the Q, exactly. And then we're going to take the h bar goes to zero limit to get the classical motion of the xi, which is GD. So that is basically, we're looking at the classical behavior in the background of a quantum field. Okay? Now, the one difference between regular integrating out and Feynman-Vernon is that normally when we integrate out things in field theory, so we have two fields. The field we integrate out, we normally fix its initial and final state. But that's actually a dangerous thing to do, because if you say that the final state has to be this, you're restricting the kinds of interactions that it can have. What you really should say is that here's the initial state, and then it does whatever it wants as it interacts with the other system, right? And so we're going to sum over all final states. That allows for energy exchange between. We know that the gravitational field doesn't just stay what it was because it picked up energy. The particles started moving, so there's an energy exchange. So it's clearly not the case that the initial state of the gravitational field is the same.
I mean, since I keep coming back to this, since M Planck is so big and the interactions are so weak.
This is where we got the confusion that we had earlier with Frank. We were like, "Oh, M Planck is so weak." But then, so I'll tell you all sorts of discussions. We thought because it's so suppressed, nothing will happen. But then we thought, well, actually, hold on. If it's very weakly interacting, maybe a gravitational wave. Most of those gravitons are just passing through, and maybe it's more like neutrinos, where there's a huge flux of neutrinos. Only a handful of us are interacting with those. And so then we might be able to see the noise. There might be a 1/√n noise, might not be 10 to the 37 that Dyson had, but only, and we had all kinds of estimates. They went as low as 600. So we didn't know what the answer was. So this is the calculation.
You can do it. So
yeah. Yes.
Some estimates.
Is there a meaning to order of units if you first take the non-relativistic unit and then expand it?
I don't think there's an order of limitation. Okay. By the way, you could also take a whole bunch of these particles, not just that two geodesic, and then you can get the quantum corrections to the Ray-Chaudhuri equation. There are whole geodesic congruence. Fun stuff. Okay. So this is what we did, and here's the result. So the effective motion we got three pieces. There's our first piece. So I want you to look at this first piece here. Is I double dot equals 1/2 H double dot times I, and compare it with this classical piece. This is I double dot equals 1/2 H double dot psi. It's always good when your path integral gives you your elementary equation, but there it is. Then there was a nice other classical piece that we got unexpectedly, but it's there. It's in Mr. John Wheeler as well. There's a classical piece, a radiation reaction force, like you have in E&M, and so there's that. But in addition, as typical of Feynman Vernon, you get something called you get this quantum noise curve. And now this piece here is a stochastic term.
Why is it? I thought it's determined by the state.
Yes. So it has. So what happened here was we are summing over final states. That's where the so basically we have, when you couple two systems to each other, one of which is quantum mechanical, and you integrate it out, the dynamics of the other one, even classically, will become stochastic. So that's a generic feature of coupling to a quantum system, that the remaining system, even though classical, will no longer be deterministic.
But so suppose I was just treating, I do the path integral.
Yeah.
So then I find an effective two contour path integral for xi.
Yeah.
And that effective path integral is just something determined. Sorry. I mean, I'm specifying the density matrix of the photon initially, and then I do the path integral with those boundary conditions. That gives me some maybe non-local action on these contours, but something determined, right?
Right.
Fixed if I knew the state.
Yeah, but the state is changed, so we're summing over final states.
That's fine.
Because a number of different possibilities are there.
That's just doing the contour like that. But you've got two boundary conditions on the contour. On this side and on that side. So you get a definite path. No?
You end up having to do a probability rather than a.
Sorry, I'm probably being this but I'm trying to understand why. Because I thought if you knew exactly what the state is, the bra would give you one boundary condition, the ket would give you the second boundary condition. And so then I can do the path integral over the photon. Your Q, whatever that was. Yeah. And then it will induce some, maybe this is what you're saying, that it gives you a two-sided action.
Yes, that's right.
And then you can do it in sums and differences. And the difference you're regarding as noise. Is that
that's right?
Now
that's right.
Because
there's a it's related to Schwinger-Kelvin.
Yeah. Now I understand. So because actually you've got a two contour path integral over the particle, but you want to convert it to something classical.
Yeah.
Classically, you have only one variable. So you break it up into sum and difference, and what the difference is doing is what you're calling the J.
Correct.
Okay.
So there's a whole.
That must be what it is. Sure, as you can, but just naively, if you're going to interact with the graviton, which has a certain quantum spread, right, then it seems quite physically reasonable that the amount by which your trajectory is affected won't be a very deterministic one.
Yes.
Right?
That's what I was thinking.
Yeah.
Absolutely. No, but just in terms of the calculation, since it's such a nice calculation.
Yeah.
Instead of a calculation with a path integral, and the calculation is completely unambiguous. There's no noise in that calculation.
Yes, that's right.
Okay. However, it's a calculation that will give you a two-sided variable for your particle. Right? Now, two-sided variable is fine if you're doing a path integral, but not fine if you're trying to interpret it classically.
Yeah.
And so classically, you'll turn it into sum and difference.
But you must go on. And you said because you're summing over final states, but just to understand, because the interaction between the classical objects Xi and Q involved Q, right?
Yes.
Now, suppose the graviton is not in an eigenstate of Q. Even if you're not summing over various states,
I don't think
wouldn't you expect to get some stochastic?
That's
not the origin.
I don't think so.
No.
I see.
That's just the regular path integral. If it's not in the eigenstate, has a wave function dependent term multiplying it on the outside. Right? That's not.
I thought because the interaction depends on the position of Q, and the Q is not a fixed. I mean, it's not a deterministic trajectory. you get some. That's how I was thinking stochasticity.
He's just
And
saying
it's-
Feynman Gordon way of
Like that, right? I think so. I mean, that just means you have a state in a sense which is not an entity.
Physically,
That's what I thought.
Yeah.
Okay.
Yeah.
Not so much emission and changing. Okay.
Okay, so the upshot of this is that instead of having xi go like this because of some classical wave, now there's also this quantum noise, and that causes this kind of shift. And this is a random function whose properties are entirely dependent on the initial state of the field you integrated out, in this case gravity. This is the Langevin type equation. And so the nice thing about it is all its properties can be exactly computed for a whole class of states: vacuum states, thermal states, coherent states, squeeze states. And you can find the autocorrelation function. You can take the Fourier transform and get the noise power spectrum density. So you can get all of this. And here's what we find, that the noise, so the coherent states and the vacuum states basically behave the same. Whereas squeeze states have an enhanced noise. The power of the noise is enhanced by e to the 2r. Okay. It's maybe not so surprising. We know that squeeze states are noisier than because they have this one direction potentially. So this is what happens. You get exponential enhancement in the noise. So we want large squeezing. Our 0.1 doesn't do the job because e to the 0.2 is not really much of an enhancement.
Oh, sorry, what is that?
R is our squeezing parameter. So we would like a squeezing parameter that's large. That was what motivated the search for squeeze states to begin with. I'm giving my results in reverse.
We are saying it's easier to measure squeeze states.
Yes,
Yeah.
because the noise there'll be enhanced noise. All right. So can we actually measure this? So here's one interesting thing about this. First of all, just naively, the noise is actually the actual noise is divergent. But there's a finite cutoff because the detector has some resolution and some maximum frequency dependence, which in our case is very low. It's like the LIGO is 10 kilohertz. But it's not inherently small. It's a bit like the Casimir effect, right? The Casimir effect, we think of it as a small effect. There's only a small effect because we've got a cutoff that's actually quite big. But if we could make the plates arbitrarily close to each other, it would be a very large effect. Right? The cutoff in the Casimir effect comes from is not inherent to quantum field theory, but to this experimental setup.
But this is the frequencies of the mirrors, right? The play. Is that what you have in mind? So the cutoffs are those, right?
Yeah,
Of
so
the classical object, right?
So here there's a cutoff of that LIGO has some sensitivity to, and which is like so basically anything that's happening in modes that are beyond that are simply not detected. So we can't.
And it probably doesn't even happen because the mirrors won't jitter too fast anyway. I mean, there's some physical cutoff, right?
Okay, so we can estimate the amplitude. So what is this? And it's something like this. Okay, so this the standard deviation in the position squared, so the variance. This is length squared. Okay, so this is the fluctuation in the mirrors, the quantum fluctuations in the mirrors. So that's a length squared. Okay, this is like delta x of the mirrors squared variance is given by this. This is the separation of the mirrors. Okay, 4 kilometers in the case. Xi naught is 4 kilometers in the case of LIGO. Omega max is 10 to the 4 for hertz for LIGO, and we're in. This is an absolutely tiny number. Okay, not surprising. Okay, but it really didn't have. It's tiny because omega max is so small compared to M Planck, and because we had no exponential.
Is the omega to the 4 because it was Q double dot? Just wondering, because that would be omega square in the jitter produced in the trajectory. And this is a 2 point. Okay, just in case. Yeah.
What was S of omega?
What is what?
The omega S of omega.
This is the noise power spectrum, which depends on the state. And this is the vacuum state times some exponential enhancement for squeeze.
Sorry, how do we know that the noise is coming from the this?
Yeah, first of all, we calculate the amplitude, then we go to how we can distinguish it from all the million other sources of noise. So here, just to be clear, there are future detectors. There's one in development at Caltech, for example, that is called GQuest. These are tabletop experiments, which ironically and beautifully are better for looking at this kind of effect than LIGO. They will see no signal, but they will see lots of noise. And that's what we want here. We don't care about astrophysical signals. The reason LIGO is so big is because it's designed to catch the astrophysical signal.
And here you assume that R is independent of omega?
Here we're assuming that R is independent of omega, which is a non-trivial and probably and certainly wrong assumption in many cases. So yes, correct. But that might change the story quite a bit.
Because the way you produced it, there was one particular R where there was a parametric, omega where there was a large R.
Correct.
Most of the others had small.
Yeah, so it's quite possible that it's nowhere near this big.
Yeah.
R increased with omega anyway, right?
R increased with T.
No, where there was a parametric resonance.
Yeah.
That particular omega.
Particular.
No, but it depended on. Oh, okay.
Yeah. Okay, so anyway, so there are two handles here to make this big. You can make omega max large by increasing its sensitivity, and of course you can get smooth. All right, finally, can you distinguish it from the million other sources? And the beautiful thing is, yes, you can. So this noise is correlated. Okay, so if you have multiple different detectors, this noise will be correlated. That already eliminates all kinds of other sources of noise. Most of the crop passing by will not produce the same noise here and there. The jitters of the laser shot noise will be different from you. And moreover,
just that the gravity or graviton has a wavelength which is big, so.
It's also because it's the same gravitational mode that the two.
Yeah, it must be tied to the size of the wavelength, right? I mean, if it's a very short wavelength, it will be independent.
Correct. Yeah. It falls off in a symbol. There's this paper here deals with that issue. But even more interestingly, if you could have a whole array of gravitational wave detectors, this is possible if they're tabletop, obviously not LIGO, then, and you arrange them in different directions, the arms don't have to be 90 degrees, but you can have all sorts of different directions. Then, because all these modes are the modes of a helicity 2 field, they have correlations that are unlike any other correlation, angular correlations that are unlike any other correlation. Because they're transverse traceless, if there's a fluctuation that decreases this one has to lengthen, right? Every mode has that property, that one side goes up, the other side goes down. So there's an angular correlation that doesn't look like the angular correlation of any other terrestrial source.
Just to get a sense, how big is this jitter compared to other sources? Because there's still a n-Planck square in the denominator. Even if, let's say, you're sensitive to gigahertz.
Yeah, without the squeezing, you're not
getting it down.
So this number for LIGO, okay, is like 10 to the minus 44. That's small.
But if you go up to gigahertz,
this is a sigma squared. So the fluctuation is 10 to the minus 22.
But if you go up to gigahertz, you win some. But it's still down.
It's still down, and this is what you need.
And so how much do you need?
Yeah, if R was of order of 10, we would be great.
R was of order of 10,
10, well, that depends on this.
More, actually. I see. But 10 orders of magnitude.
Around
10 to the 10, yeah.
That's it.
The Planck scale depends the same as the signal itself, right? I mean, you're looking at the jitter and the gravitational wave.
Yeah.
The gravitational wave itself was also 1 over m Planck squared.
Yeah, but it's enhanced by the mass of the black hole that is producing it, right? That part will be g times mass, right? That's how I was thinking. Maybe my estimates are all off, but I thought that would be, okay, the standard signal, small, but this would be, the frequency cutoff dependent. Am I wrong?
I thought that both of them would be set by the frequency of the orbit.
Also the mass, right?
Mass? No, it's just, the calculation he's done is just this, something's orbiting.
Yeah.
The orbital frequency that sets the
But the
and
source,
mass of the source, that also affects the R thing, right?
For example, if it was a cosmological signal, okay, like Rishuk type thing, right, where the R is of order of 60 or 100 or something, then it's hard to think of it in terms of something orbiting. It's just the expansion of the universe.
Yeah. But okay, say R was order 10.
Yeah.
Is then your jitter roughly comparable to the signal?
To the signal?
Signal. I mean, you want to measure the. I mean, how does this compare with the amplitude of the signal spectrum?
Well, for the cases that we're interested in, there's no signal at all.
Why not?
Because we're going to look in very high omega frequencies, where we're hoping to just see squeezing in the vacuum.
But suppose I was doing it for LIGO for a moment.
Yeah.
Okay, but there is a signal.
Yeah.
There would also be some, according to your calculation, also
then I don't think we'll get any. Which I mean, I just did the calculation saying the R is very small for that case, 0.1. But in addition,
so is there some parametric suppression between signal and your jitter? What parameter suppresses it?
There doesn't have to be, in general, a suppression between signal and noise.
There is not, but you're saying just the numbers align so that it does.
In the case of the infalling one, there was only one parameter.
Yeah.
And so it was sort of where you start the Newtonian potential, which both dictated what the amplitude was,
signal
and
as well as
how long it's
there was no parameter. So,
but to give you a different example, supposing instead of having it fall under its case of gravity, you had in my lab, I took a little rock and I just swung it like this for forever. Okay. And so that produced very little in terms of gravitational waves because it's just a 100-gram rock or whatever it is. But eventually there'll be a buildup of
just because you're doing it forever.
Because I'm doing it forever, right? And because I'm sourcing it with energy.
My intuition comes that wrong, right? But please correct me. I mean, so let's say the gravitational wave passes by and the two mirrors respond by changing their distance.
Yeah.
And then there is the quantum jitter on that, right?
Yeah.
And even if R is produced at its source by G Newton times M, the quantum jitter has got to be small for a heavy mirror, right? As it responds. I mean,
the mass of the mirror doesn't factor in by equivalence principle.
I see. But I mean, shouldn't the... So
let me just finish.
Oh, yeah.
2 slides left.
Oh, yeah, please.
And then we can... So anyway, the punchline is this. The signal of quantum gravity is in the noise, or at least one signal. And, to recap the whole story, we were looking for signatures of quantum gravity. We saw a loophole inspired by quantum optics, saying that, we don't need loop suppression if literally a loophole. If we have an exotic state, okay, and then we first calculated how are we probing gravity? Well, now we have these nice interferometers. There are of course other probes, Weber bars and whatnot. We could imagine, but we looked at the one we had, and then we said, what is this doing? Well, these mirrors are basically. We did the physics thing by saying, LIGO is 2 particles free falling. And those are the mirrors. And then we looked at the geodesic deviation, which is a gauge invariant thing. We saw that it was sensitive to the noise after using Feynman-Vernon. And we realized that noise is generally very small, except because of 2 things, because of Planck's mass and also because the cutoff frequency is very small because of the sensitivity. But we found that it was state dependent. It could be dialed up with an exponential if they're squeezing. Okay, and so this was how we initially presented it. And then everybody came back and said, why should gravity be squeezed? And the intuition that squeezing was something exotic came from E&M, where it is something exotic. But then we were trying to think about how squeezing comes up generically, starting with the harmonic oscillator. We saw that any quadratic term typically produces squeezing, which grows in time because of something similar to parametric resonance. And therefore, since gravity is full of these quadratic terms and more, we would naturally expect it to be. We calculated.
Rishchuk then was thinking about squeezing.
It was 1975. Yeah.
So this connection was already kind of established
Yes.
between the squeezing and gravity.
I mean, everything in inflation is
Yeah.
a steady state. It is a standard calculation.
I see.
So the correlation between the jitters in the two arms, that's very special for this restless spindle move. But would one expect statistically a certain amount of correlation even from thermal noise in the two arms?
Yes.
And would that not dominate the very small bit of correlation that you have?
You're surely, I'm sure you're right. This is far beyond what the kind of calculations I'm doing, whether it's reasonably, in principle, if you took n of these, for example, you'll still see if you had a whole array of detectors, you will see less and less correlation for the other one.
That was exactly when I was asking how big the jitter is, right? Because you have these standard sources of jitter.
But there's more. There's there's also a particular power spectrum. So beyond the correlations, there's actually also a power spectrum. That power spectrum doesn't look anything like a typical power spectrum of noise power spectrum. So there are other ways to distinguish it besides the angle of correlation. Okay, let me end with my punchline here. The noise is a signal. This is, and there's a whole history in physics where we've learned a lot by focusing on the noise. It was Brownian motion that led Einstein and Smoluchowski to conclude that matter is in fact discrete in terms of molecules. It was shock noise and fractional in electrons that led to the fractional quantum Hall effect, and it was excess radio noise discovered by Penzias and Wilson that told us about the Big Bang, and we're hoping that if we find detector noise, that will tell us the discreteness of space-time. So we should not. Noise is where the most interesting things are because it's something happening that we're dismissing as noise, but usually there's physics there. Thank you.
Usually, so you have been able to figure out the noise exactly from the first principles. Usually, you do we never do that, I suppose, right? The statistics of the noise you have been able to figure out by this path integral thing.
I mean, depends on what in gravity, it's a very clean system because we know exactly what the actions are, we know how the couplings are.
Usually, you
there's any
model the noise, right?
Yes.
But here, you don't know what the noise is, but you have been somehow able to figure out exactly how the noise statistics should be from the path integral itself.
Well, the uncertainty is mapped onto what the state is. So if I tell you what the quantum state of the gravitational field is, I can exactly tell you what the noise is. But you might have a lack of knowledge about what that state is.
So this is true for any quantum system, including the gravitational state.
Yeah, so Feynman and Vernon have a method where if you know the state, if you have two systems, and you know the quantum state of this one, you then integrate out over it, and you know their interaction, you can tell exactly what the property of the noise.
Just one comment, maybe that is quite commonly done in condensed matter. Like his example of short noise and fractional quantum Hall. The whole statistics can be computed and actually has signatures. So what you are saying probably is not true with them.
Can we just come back to this formula you had for S, the power or whatever, finally after the Maulik learner? Sorry, I'm still confused about the M-plax, okay? Because in the equation you had, which was, how the mirror was responding to Q double dot, already there was a M-Planck square, right? Because it was G Newton effect, I mean, the leading effect was a G Newton Planck effect. Now, in the 2 point, so now the reason I was wrong when I said, it's suppressed by mass. No, it's not. But noise averages out, right? So it should be a 2-point correlator.
Yes.
But shouldn't it be down by 4 powers of n plus? Each of them is down. This is a XX for the mirror, right? This sigma square is a 2-point, right?
Yes.
So each x is down by 1 over m. X is q double dot over m Planck square, right? So why is XX not? This is where I was thinking.
2-point function of E.
Yeah. The 2-point.
1-point function.
Yeah. Am I wrong? I must be wrong, but this is where I was wondering that it should be smaller.
Let me write it this way. So I have x equals x classical plus x fluctuation. Okay. Now x classical has the m Planck in because it's responding to equation motion. And so now if I take this operator and sandwich x squared in it, I will get x classical squared plus a linear term, which is x classical x, plus an x squared term. The linear term x classical x, I think, probably gives you another x classical.
Yeah. I see. You're not taking the fluctuation about x classical. Yes.
And then, but the last one doesn't have any m Plancks in it.
What was the last step? Sorry.
It's just the fluctuation part. So you have.
I was just thinking x minus x classical will already have a 1 over m Planck square.
That x classical is in the one. The m Planck is in the x classical. Not in the.
But if I measure just a time series of x to get the noise, that's just 1 point. I'm just measuring one x, but it moves around.
But it'll average out on the frequency.
It will. But I'm actually measuring a time series. I see it. And I see it move around at order 1 over m Planck.
But this is XX. Maybe I'm confused. Sigma square is what? Isn't it XX correlated as a function of omega?
Yes.
Oh.
See, so now don't you think that's a bit strange?
Yeah. Now I'm confused. Wait, so I thought that as Sandeep was saying, that the average fluctuation of your noise would be 1 over m Planck, of your position would be 1 over m Planck square.
Yeah. So the 2-point, that's what I was also thinking.
Yeah. Then now,
average fluctuation
meaning you take a time series, you look at how much it's fluctuating. That would be 1 over m Planck square.
Yeah, that I agree.
Yeah.
From x classical, if you take the root mean squared, that would be 1 over m. Maybe but
no, that's not right.
Is that so? You're thinking of it as short noise, or
no? Just that the noise is created by G.
Yeah, G exactly. I agree that it's created like the classical part. That part I agree.
So both the classical part as well as even the signal square would be 1 over m Planck.
Yeah. I agree with you. But it's a bit puzzled.
So even the signal square.
But maybe you're dividing.
This is the variance, right?
This is the variance.
Yes. So
2-point, right?
You were saying that that should have been omega to the 4.
No, n to the 4. Sounds
maybe it takes 100.
Sounds right.
Maybe I'm missing.
No, I think it sounds right. I think even the signal square should be m Planck.
Yeah, that I agree with you.
All right, I might have.
Okay, never mind. Okay, that's fine. I see, but very interesting.
No, but I mean, roughly, I think he's saying that there are situations, if it's all right, where if you can measure the signal.
Yeah, the variance, the standard deviation is the same order. Yeah. That's what's interesting. We got a little bit hit by some omega.
But this question about the locality seems very important. Because that's what allowed R to become order 1.
And that is.
Yeah,
okay, so if the R was also itself suppressed by 1 over m Planck square, then it is a second.
Yes.
So that is a
But I would say do it in inflation with parametric effects. You guys haven't thought of that. Sorry, but that's the natural thing I would do. Because, there you know cutoff. There the oscillator example is you're in there.
We're looking right now at still the example that we do have direct access to, which is black hole mergers. to see whether if you make the orbits elliptical or in the merger phase, there's enhancement. So right now we looked at a very simple one, and there is an enhancement by eccentricity. So the more eccentric it is, there's like a 1 minus eccentricity squared in the denominator. I don't remember what power there is. So E was 1, there'll be a expand rate enhancement. Yeah.
And we'll see this in conformity theory in anti-disk space.
Can we see this in conformal field to analysis?
No, in anti, so that's why in conformity.
Well, this is perturbative quantum gravity, right? So there's no particular reason to put it in ADS, I think. Is it?
It's dual to conformity theory.
I guess you could.
You want to interpret it as a phenomenon.
You want to interpret it as
Some universal expectation about the 2-point function stress tensors. We basically try to get to the nonlinearity.
So we need a time dependence. We need time dependence.
Yeah, so you look at time dependent state, conformity theory, and then.
No, you start out with a vacuum state.
Okay.
And then so ADS ground ground state, and then you have a source that is time dependent in the bulk. Okay, that will produce this kind of squeezing. You can do things very simple. In fact, this simple accelerating particles might be the easiest one. Okay. Then we even know that it's going to give you some Rindler-like radiation, but then there will be squeezing on top of that.
Hey, one organizational question. Are you free for lunch today, Maulik?
Sure.
I mean, we could take you out if you're free.
Yeah, you can.
So we'll go, not to stop the questions, but we go out for lunch.
I was at this cafe, Subco, Colaba. It's amazing. You know what this is?
What is it? Cafe what?
Subco? Wow.
Where is it?
Yeah.
Right, you should come more often. So
It's on a place called Second Fasta Lane.
Oh yeah.
I didn't even know there was a street like that. But
There's also third in Paris.
imagine
So-
Where were you?
Huh?
Where did you go?
Not far. Not even far.
What else are you folks thinking about besides the in-spiral to look forward?
I mean, basically any kind of phenomenon where there's time dependence, whether it's cosmic strings whipping or, there could be if we see, the nice thing here is you can exactly, in principle, calculate the power spectrum of noise.
Okay, but sorry, knowing your collaborators, since
Yes.
the needle has moved to axions being the most likely source for dark matter.
Right.
It's no longer cold dark matter.
Yes.
Is there a scenario in the early universe? I'm just asking if you've thought about this. It's a sort of natural question, right? I don't know if it does that. Inflation would be what I would think, but I'm wondering if you guys thought.
So the same techniques can be used for any fields, right? We're interested in gravity just because it has no signature.
Right.
But we also have no signature of axioms. So we could have thought about how do axions couple to ENM, and then maybe time-dependent axionic fields will be squeezing in light.
No, but I mean for gravity waves, but there's dark matter also. And does that? Can you get a parametric effect? Maybe in some scenario, but let's assume you have axions or something, and you have a parametric effect. I'm asking if you guys have thought.
No, there are a million times kind of benefits. So, we've also talked to experimentalists. That's quite a culture shock for me, but they're asking. These are not their variables, so they're looking at observables that are time difference.